Most of the work that I'll present you today was performed at the Oxford Center for Drug Delivery Devices. But as Tom mentioned, I've recently moved to the Imaging with Light and Sound Institute, and these places, I guess, kind of also gave away my motivation. So I've been trying to apply the kind of ideas we are discussing here for therapeutic and diagnostic applications. So I'm very much concerned about the complexity. But before that, I would like to give a quick recap of what I've done previously. So basically, this all started when I was a PhD student with Matthias, and this you have seen. But I feel like in all the excitement about seeing these pulses, we often understate the incredible optical phenomena that allowed us to see these pulses. So I just wanted to make a brief statement about that. So essentially, what we used in this setup, which Kevin actually explained quite beautifully yesterday and showed it in all its glory, that you have these two fluorescent dyes, just normal dyes, nothing special about them. They can float around in the lipid membrane, lipid monolayer here. But when you put them together, they do something very interesting. They do this phenomena called Foster resonance energy transfer. And the idea is that you shine blue light on one of the dye. It emits in yellow or green. Part of that light goes to the detector, but part of it goes to the another dye which is sitting next to it, right? And then that other dye basically absorbs some of it and then emits that. So you get two different kind of emissions from your monolayer, and that is basically the signal. So that ratio, that efficiency of that process, and it depends on both on the distance between the two dye in the system and their orientation with respect to each other, right? So so basically, when you see this signal, these dyes are literally doing something like this. Okay, so there are related motions, and you have to imagine that there are millions of pairs like this in the monolayer. And in my humble opinion, I think it's very difficult to think of this from a molecular perspective, as long as you don't think about the music in the monolayer, as Connie put it yesterday. But yeah, I mean, but since then, so that's what I want to say about this phenomena. But since then, I've kind of made a similar setup, or have been making similar setups with more faster time resolution and more sensitivity. But the basic idea has remained the same, and which is that in all my experiments, basically I have a sample where I can put all sorts of things. There will be an acoustic perturbation, which I can define very nicely from outside. It goes to the sample, and then there are some kind of optical emissions from fluorescence emission that I can record, and then look at how the spectra changes. And from this delta P over delta A is basically the thermodynamic property that I'm trying to measure in all these experiments. So at Oxford, what I've been doing is moving from 2D systems to 3D systems, and now it's a very similar experiment. You can imagine these vesicles floating in the liquid, and then I send these shock waves. Notice the time scales here, these are microseconds. And we are interested in this phenomena because now we are thinking about how we can use ultrasound and shock waves to affect, for example, membrane permeability or cause neuromodulation, as this is like it's an upcoming field. And we want to understand what happens at these time scales, because these short time scales have not been really looked at. There was no reason to look at them before, I guess. But what I realized, or what I kind of knew already, that I have to move away from the fret system for various reasons. It was one of them. It wouldn't have been fast enough. So then I moved to this really old, well-established system of this dye, Laurdan, the kind we heard earlier today. It's basically a very similar dye, and what it mainly does is changes its color. As you go through the transition, I will not explain too much because I think you have heard about this enough. But the color, in this case, you can think of in a very general sense that the color of the dye is an observable of your system, and it does everything similar to what all other observables do. And so we see this shift in spectrum, and if you notice at this dotted line, which is basically the phase transition in your system, you can imagine that for very small pressure and temperature fluctuation, you would expect a big change in color. And so the thing we thought, or the question was, could the width of the emission spectrum be related to these fluctuations? And if you follow that thought and just play some analytical games, kind of along the lines of the derivation of black body radiation, you can actually derive just with one phenomenological constant a specific heat for the membrane from the dye. So the question is, of course, I mean, you get something out of this, but is it really a relevant thermodynamic susceptibility of the system? So now, because I have acoustic perturbation, I can test this and just perturb the system at different points and see what the response is. And well, it does exactly follow in terms of amplitude, starting from all the way here, you almost see no response, then response slightly increases, goes through a maximum, and then dies down again. So this one is quite far off in this diagram. And so what basically you are seeing here is that you can do this whole exercise from going to state to a response within the space of an optical parameter. So at least for lipids, what you can do is that you can put this dye, see the width of the spectrum, and from that predict what will be the perturbation of the membrane when you hit it with an acoustic pulse. And this was not just in one single lipid system. I did mixtures of lipids, different lipids. So here I have represented them as a general parameter of reduced temperature. So it's in terms of their distance from the phase transition temperature. But you might notice that the signals are not as pretty as you saw in the monolayer. And one of the reasons for that is, I mean, the time scales here are really fast, so actually they were literally quite small perturbations compared to what we see in action potentials. But the other thing is we could have tried increasing the amplitude of the pressure, right? The problem with that was, okay, sorry, I added the slide after in the morning after discussion with around the optical probes. So I just wanted to mention an aside. This is an experiment that Tasaki did using the same dye, or an sister of the dye that you saw earlier. And what he noticed that when you excite an action potential in nerve fibers, they undergo a spectral shift, the kind of experiments you were seeing earlier in the morning. And what he noticed also that the solvent polarity is known effect, and not just that, the maximum emission, but also the half bandwidth of the emission spectrum changes. And this is relevant because we just saw that from the width of the spectrum, you can actually extract the compressibility of the specific heat. So what this experiment is showing you, that the membrane is actually getting stiffer. This question is not in the picture anymore if it's potential or state. You are actually measuring the compressibility, and this applies to all dyes. So the treatment was very general. You can have a potential sensitive dye, pH sensitive dye, doesn't matter. This is what you get. So just coming back to my original talk. I was talking about why we get such small perturbations, and the reason is, like, if you try to increase our pressure perturbation, something else starts to happen in our medium. So now we don't just have only the lipids now, we have water, and it starts to cavitate. So this was a problem, but also interesting, because now it seems that if we want to control the state of the membrane, we need to understand how to control this. Because this doesn't happen, I mean, this actually happens at clinically, people are trying to use this phenomena already for clinical applications. And I have a poster on this, I will not go too much into the detail, but the idea is, or what I observe in short, is in the presence of lipids, what I notice is that the phase transition, or basically the cavitation threshold now for the water to vapor transition, is minimum when the lipids in the solution are near their phase transitions. We have two phase transitions here. One, that water goes to vapor when the negative pressure pulse arrives, and that's a totally different transition. And then we have lipids in the solution, and you can play around with them. So at fixed temperature, you can bring in different kind of lipids, which are in different states. And what we find is that the threshold for cavitation is minimum at the phase transition of lipids. The other thing, which was very interesting, is that now you might imagine that an expanding bubble is almost like a spherical language trough, which is sensible to a certain extent, but in this system a lot more is happening. And so essentially when you're expanding really fast, you have lipids all around, and then they start to pile up. So that's one thing. The other thing that's happening is you have water to vapor phase transition at the boundaries, which requires heat, latent heat, and that also has to come from somewhere. So again, I explained this a lot more in my poster, but effectively, it seems that depending on the rate of expansion of the bubble, you can either crystallize your lipids or fluidize them. So in one case, when you're expanding really fast, it's the same adiabatic decoupling kind of principle we talk about in nerves. The heat has to come from the interface and is extracted from the lipids. And when we expand it slow, then it is fine. It almost works like a Lambert trough. So just to conclude from the previous slide, a picture like this emerges. So when you have nothing, no acoustic perturbation in the system, your lipids are floating around, there are fluctuations happening in the membrane, and every now and then there are fluctuations happening in water, which creates these vapor nuclei. And we imagine that these two fluctuations kind of interact with each other. And that's why when your lipids are near phase transition, you get these lowering of the threshold of cavitation. And then once one of these nuclei appear, the shock wave latches onto them and expands them violently, and then you have all these kind of piling up on the surface of lipids and heat extraction and so on. So this was all good, but before I came up with my dyes, that field was doing this for a long time, right? So they had their own observables, and I wanted to understand how we can maybe extract from the conventional observables what can we learn about phase transitions. So these conventional observables were just looking and hearing what happens when a bubble collapses. And this has been in the field for a really long time. And so, to my surprise, usually you read in these books you would read about emissions, of course, and then the idea is then the bubble expands and it collapses. There is sound because of this collision of the boundary. But what I noticed is, so here I have the acoustic signal in blue, and in red I have the optical emissions. There's no dye now, right? So there's no light, no dye. It's just natural emissions from the system. And as the shock wave arrives at the focus of my setup, there are emissions at the beginning itself. And when the cavity starts to form, at that point itself, there are emissions both acoustic and optical. And when it collapses, there are emissions as well, which was okay. So I ran to my advisor, I was like, this is great because this seems that we have found something which is currently not explained. And he was like, no, we know this for a long time, and we assume that basically there are these tiny bubbles in the water always floating around, and then the shock wave comes in, it crushes them, and that emits the light and sound. And this kind of didn't satisfy me because this is quite significant, and for this, the claim is that you need this big bang, and somehow for this, even the short bubbles can do that. So I kind of tried something else and tried to time these events. So basically, now in this experiment, I put a light and try to look at the scattering. So what now I can do, I can look how the bubble is expanding in real time, and when exactly the sound is coming out. And when I did this, you can see that the sound is actually being emitted in the phase when expansion is already started. So this black curve here shows how the cavity is expanding. It's basically the light scattered from the expanding cavity. And you can clearly see this arrived later, but my boss was still not convinced was still not convinced, so I escalated the situation. But yes, no, I'm just kidding. So then I introduced one more observable. It's a tactile. Basically, you measure the pressure right at the point and try to time it and see at what point is the light and sound coming. Is it during the compression, in pressure, or expansion, or negative pressure?
Is that a representation of your boss or of yourself?
Myself. Yeah, it hurts. Yeah. So, and you see, so now this is actual pressure measurement at the focus, and So I timed it really, tried to time it really accurately, so there is not much deviation in the time when the shock wave arrives at the focus. And here you see solar luminescence from 80 different collapses, and none of them happen during the compression phase. So it is clearly happening during the expansion phase of the bubble. And I can do a lot of different kind of correlations because I have so many observables, but I'll just show one here. So the acoustic emission that I see during the expansion of the cavity directly correlates with the expansion rate of the bubble. And that kind of fits the narrative. So the idea here is that and what we basically think is happening is the emission is coming from this boundary. That is the only way to explain this, and I can go more into detail in our discussions later. So that's interesting, and the way I started thinking about it is in order to have this vapor to liquid transition, you need a lot of heat. And this heat has to be transferred. Now, transferred within the medium, so there's internal heat transfer required. Now, usually we assume things are quasi-static, so you do not have any kind of dissipation involved, but I think the more general assumption is to not assume that, and so we can say maybe, and especially given the time scales involved, it's likely that the internal heat transfer is happening during non-equilibrium condition. And once you have that, you have emissions and dissipations. This is well known. And so this is not the dissipation, the kind of dissipation that you get from friction. I'm talking about what you see in the Carnot cycle, that if you transfer energy across a gradient, then some of it will be lost. So coming from that perspective, and then there is the symmetry problem. So if this is happening in this direction, it should also happen coming back. So we are now moving towards this phenomenon called solar luminescence. So when it collapses, what is the mechanism that for which the light comes out, right? But there is, so this is just my last slide now after this, but basically I wanted to say that so you already see that in one case the heat is leaving the system, in the one heat is coming into the system. And to kind of just explain a little bit about how these two conditions are slightly different, and we have seen this diagram many times in the last 2 days. Stick with me just for this last slide. It's a little bit dense, but yeah, it will be worth it. So usually we see this dotted line that in many presentations, which represents the isotherm. I mean, you can represent it in terms of P and B. We saw it in terms of pi and A. And in our experiments, we fix ourselves somewhere here, right, at this point 1. But what happens during a pulse? It's not that clear actually, because we can say that it goes through somewhere here and lands somewhere up here, but it definitely doesn't go through this part because that is determined by the process, like what path is exactly it gonna take. So between the two world wars, actually physicists figured out a really simple way to do this, and that is, you heard about conservation laws. So that in order to find what these values are, you basically need to apply conservation of momentum and mass. And for at least for one-dimensional system, you can combine those two conditions, and it is represented by a straight line on this curve. So it looks something like this. Oh, that could be a path, for example, and then it would look something like this. So the solid black curve is imaginary. We imagine it goes through somewhere like this. But this straight line it's the condition of continuity and conservation of momentum. It doesn't represent a path again, but it tells you what the initial and final state of the system should be. This is known as the Rankine cubenoid condition. I think I pronounced it correctly. Yeah, and so we talked about pulses, lipid monolayer, and it's similar to what Martin talked about yesterday. So it's kind of trying to find solutions, and Martin showed really nice characteristic curves on these things. But here, the monolayer goes from this direction to this direction when we're talking about pulses in the monolayer. But when we are talking about cavitation, you can think it's actually going from this point to this point. So in this way, they are kind of related, especially given that Martin talked about this relation to van der Waals fluids, and that basically fits in that picture. So, and just now trying to explain what happens when the cavity is collapsing. So you have this vapor cavity at the center, and there is this metastable region basically where you have a superheated vapor. It's trying to go undergo the transition into liquid phase but hasn't reached there. So it is some intermediate limbo region, and that's represented by this light blue curve. And then finally you have the liquid phase, and this is trying to collapse. Now the interesting thing here is that at this boundary between the metastable state and the liquid state, that's where phase transition happens. And because vapor to liquid transition is exothermic, heat will be released at this point. And if you can compare with this curve, we can actually extract that. It's not straightforward, but you can extract that the velocity of sound here will be higher than the velocity of sound in front of the pulse. What that allows is actually the heat that is emitted behind the pulse travels to forward and reinforces the front of the wave. So what I'm actually trying to explain to you is the mechanism of detonation. And this explains a lot what we see in collapsing bubbles. Again, that's a little bit longer conversation, but you can take my word for it for now that I do think that this is really something that is involved and happening here. And funnily enough, this, I think, as I was just mentioning earlier, relates to what we see in the monolayer, because water can also be represented by a van der Waals fluid, which Martin showed, can also be used for lipid monolayers. And in fact, this fine structure I talked about, like the vapor front and then a metastable region followed by a liquid state, is also seen in lipid monolayers. So this is an experiment we did in 2015, and that kind of motivated me to start reading about detonation, because I wanted to find an answer for what I see here, but was not very clear at that point. So what you see here is how the pulses in lipid monolayer that you saw earlier behave as they propagate along the distance. And the important thing to notice here is at some point they start to split, and then the front part, like the front part bit here, maintains its amplitude, but the following part actually starts to decay. And this is kind of evidence of the idea that the heat is traveling from back to the front, and that is what it makes it self-sustainable for quite a significant distance. Yeah. Okay. So I skipped the conclusion. I think I concluded many times during the talk, but I would leave the talk with these slides and these quotes. So thinking about detonation, and it's amazing the kind of work that was done and sounds so resonant now with the kind of discussions we have been having about, is it electrical or mechanical, is it chemical or mechanical? And so if I go to the first quote, we are disregarding the possibility that detonation is propagated by a special kind of particles moving ahead of the wave head. Indeed, if the views which we propose are found to be correct, no such special particles will be needed to explain the detonation wave. And independently, Zelovic in Soviet nuclear program said, finally entirely inadmissible at the present time are the attempts to identify the velocity of detonation with the velocity of motion of any particular molecules, atoms or radicals in the products of combustion, the corresponding particles being assumed active centers of chemical reaction chain. However good the numerical element, such an attempt is no more than a makeshift and a clear backward step with respect to the thermodynamic theory. And with that, I would like to end the talk. Thank you.
Next speaker, if you could get set up right away, I'll take just one little question. And before I take the question, don't leave in a hurry, because after the last speaker, there's a picture that Mathieu wants to take of all of us. So I'll take one question. Yep.
I have one question on your computation threshold as function of your normalized temperature. How cold is your normalized temperature? Are you in the ripple phase or below? And can you explain why the threshold is higher in the fluid phase than in the tube phase?
Oh yeah, so the question is, in the x-axis of my threshold diagram, I show these different temperatures, normalized temperatures. What state do they exactly represent? And why is the threshold higher in the fluid phase than in gel phase? So, first of all, I mean that range is not very. So the leftmost lipid is DOPC, which has a phase transition. Oh, sorry, rightmost, like the fluid most lipid is DOPC, which is minus some say minus 12 to minus 40 degrees Celsius phase transition. And the rightmost is DTPC, which is, so that's the range. So these are like usual lipids that we use, and they were done all at room temperature, so around DMPC phase transition, so that's the middle one. And we see that the phase transition is minimum for the DMPC lipids. Yeah. And the other question was about the ripple phase.
Yeah, why the threshold is higher in the fluid phase than the...
Yeah, that is not clear to me. I mean, it's minimum at the phase transition, that is clear observationally, and we can explain that also. Why is it clear higher in DOPC? Maybe I need to try some other lipids, because DOPC is slightly different from DMPC, and maybe it's a big difference that it has to overcome, because it's really far off in the fluid. So yeah, that's that I don't clearly understand. Yeah.
Okay, well, thank you very much, Shamit. And Florian is going to present